Then 5, the operation of subtraction is the inverse of addition. Just like in case of real analysis, in case of real variables, we have Z1 minus Z2 is equal to Z3, then we can write Z1 as Z2 plus Z3. Okay, means if we add Z2 over here in this, on this side, and Z2 on this side, we can see that on the left hand side minus Z2 and plus Z2 becomes 0 by the definition, and this is Z1 is equal to Z2 plus. So subtraction is nothing, it's just inverse of the addition. Division is the inverse of multiplication. That is, Z1 over Z2 is equal to Z3 if Z1 is equal to Z2 and Z3, provided Z2 is not equal to 0. Provided Z2 is not equal to 0, then it is just Z1 is divided by Z2 is equal to Z3. That means Z1 can be written as Z2 into Z3. This is very strong condition over here, that Z2 should not be 0. If it is 0, then it is problematic. Then we have commutative laws for addition and multiplication. The commutative laws are Z1 plus Z2, Z2 plus Z1. This is commutative with respect to addition. Just in case of real numbers, 2 plus 3 is the same as 3 plus 2. Similarly, in case of complex number, it is commutative. And Z1 into Z2 is the same as Z2 into Z1. This is commutative with respect to multiplication. Then law of associativity, that is associative law for addition and multiplication. That is, if we consider 3 complex numbers, then this way of addition is the same as this way of addition. That means first we add these two numbers, then Z3, or we add these two numbers first and then Z1, the answer will be the same. Similarly, Z1 into Z2, Z3 is Z1, Z2 into Z3. So this is associative with respect to multiplication, and this is associative with respect to addition. Then we have distributive law. Law of multiplication over addition. That multiplication is distributive over addition. That Z1 into Z2 plus Z3 can be written as Z1 into Z2 plus Z1 into Z3. So this Z1 is distributed over Z2 and Z3. Okay, this is multiplied with this plus this is multiplied with this. So Z1 is distributive. Now we come to the geometrical representation of complex number. As said earlier, that it needs a plane to be represented. This is x-axis, are also called real axis. Real axis. This is y-axis, also called imaginary axis. Then if we have this point, this x plus iota y, that means if this is an ordered pair basically, then the complex number is this vector emanating from the origin to this point. So this is a complex number. This, if we consider this only, then this is just a point. So the point is considered in R2, whereas in complex number we consider this vector. We don't call it vector as such because this is just representation of the complex number in terms of vector, but it is not a vector in that sense, because if we call it vector, then the division of vector is not defined. You know already, I think. If this is a vector, okay, this is a vector. Vector cannot be divided by another vector. This division is not defined. You know, I think. However, the product of two vectors, either it is cross product or it is dot product. It is well defined, but division is not defined in vectors. So if we cannot say that this complex, if complex number is considered to be vector, then we cannot define this. Okay, so this is a vector. This is vector in not a true sense. It is just representation of the vector. Okay. So this something like this. So there must be the magnitude of this vector. That magnitude is, if this is z, then the magnitude is this one, and it is defined as x square plus y square under root. Means the length of this vector from 0 to this point is defined as x square plus y square under root. Okay.